I told you that I went home and apologized to Caitlin. It's like, my God, I'm so sorry.
You have to listen to this all
I
the
am
time.
all the time. And she said, "That's you don't even know." Welcome back to Leaf, a LI-COR plant physiology podcast, all about taking great leaf level gas exchange, the mathematics, the physics, the biology behind it all. It is now episode 4, and that's right. Not only do we have new intro music, which my guest loves as he rolls his eyes, we got a new guest. And today, the short straw was drawn by Dr. Doug Lynch. Hello and welcome to the podcast.
Hello, Seaton. It's wonderful to be here.
Doug, why don't you go ahead and introduce yourself to the large audience that is Leaf to Leaf.
Hello, everyone. My name is Doug Lynch. I'm a principal scientist at LI-COR, focusing mostly on leaf-level plant physiology instrumentation, and I have been at LI-COR for now just over 11 years.
11 years?
Yeah.
Wow, you're kind of getting up there, Doug. So 11 years. Have you always been in this type of position at LI-COR?
No, when I first started at LI-COR, I was in the science and support group. So I was handling troubleshooting with customers for the first half of my career here.
Nice. How long did you do that? Did you already say?
I don't think I said, but I did that for maybe 4 or 5 years.
So that's kind of great. Starting dealing with a lot of customers and use cases, and now kind of into the completely into the R&D side of things.
Yeah, that's right. Having that experience gives you a lot of perspective on the types of problems that users typically run into to aid in making instruments that can, help users more easily troubleshoot problems and make better measurements.
I'll go and say it if I say former user, I sound like a recovering drug addict. But from a grad student's perspective, we can't really trivialize the amount of help, like godsend, that that entire group is. So thank you for doing that for so long. And now I get to work a little bit closer with you on the R&D side of things. But what I think is really cool about how you got here, both starting where you're at now, is like the journey to get here at LI-COR.
Sure. So I had a first career as a electrical engineer, so that's my undergraduate degree, and I spent 5 years working as a double-E, designing lighting control systems for a company, and realized engineering was not my cup of tea, and got more interested in plant science, so decided to go back and give graduate school a go, and so I have a master's degree in plant biology and conservation from Northwestern University, which is a really cool joint program with the Chicago Botanic Garden. And then from there, moved on directly into a PhD at the University of Illinois Chicago campus, where I studied carbon turnover in fine roots using one of the FACE systems, or free air CO2 enrichment systems at Oak Ridge National Labs was my study site.
Nice. That's a pretty cool site.
It was. It's a very cool place. Yeah. A lot of interesting science came out of those FACE systems. Yeah. And then after completing my PhD, where I actually used some LI-COR instrumentation as well as lots of other instrumentation, and having the engineering background, I realized that instruments was kind of a nice sweet spot for me, where I can help contribute to scientific endeavors, but also get to do some, to me, interesting engineering work as well. And so this has been a great fit for me.
So you've done a lot. You come from different type of background, a lot of engineering, a lot of experience in the field, and both above ground and below ground things, which is pretty awesome. I gotta shift gears a little bit here so people get to know you even more with just some what I have termed fun background information about Doug. So we'll just go ahead and start off. This will just be kind of quick. So favorite book. I think I know a lot of the answers to these. I only have a few, so don't worry.
Okay.
Favorite book.
Favorite book would be Dune by Frank Herbert.
Not surprised. heard so much about this. Favorite.
For listeners out there, it's a book where ecology is one of the main characters. So give it a read.
Believe it or not, Doug's not even getting paid to advertise. Okay, so Dune, yes, of course. Favorite movie?
That one's a little bit
I
tougher.
thought you were going to just go for Dune again.
No.
But David Bowie.
No. My kid's favorite movie is Dune. Favorite movie? Based on rewatches, it's got to be The Big Lebowski.
I see. I always knew you were
Is that
smart,
appropriate
Doug.
for these?
Is that well, I don't know. Educate. Go get some culture.
Yeah.
Okay, read Dune. Carve out, half a year to read that book, and then watch some Big Lebowski. Maybe you'll understand some more quotes from Doug. Last time I asked both Rich and Jason about nicknames. You have a nickname. Are you willing to share with
I
folks?
mean, there is a nickname that some people around here
Right.
refer to me as Dougie Fresh, I believe is what you were looking for.
Right. And you can point the finger and blame someone for that nickname.
Oh,
Like,
that's
this is the
absolutely
platform.
Mary Jo. Yeah.
Yes, MJ. Very fair. But yes, Dougie Fresh is used constantly throughout the office and beyond.
Not have to worry about that editing.
Dougie Fresh, don't you worry about it. Don't you rest easy. So throughout this episode, I'll have some off-topic questions about Doug's favorite book. So we're going to kind of test his knowledge not only about this chapter that we're referring to in the episode, but also Dune. So stay tuned. But before we get into that, we've got this book, right? That's the whole reason that we have this podcast, and we've talked way too much with Jason and Rich. I think we're all bored of them, but maybe you could highlight what your role was in this book.
So I served as a editor and provided feedback on, I think, pretty much every chapter. Mm-hmm. And some of the data sets in here I helped collect as well. So some of the figures that are redrawn was data collected by me.
Nice. Do you have a favorite chapter? It doesn't have to be this one.
For sure, the chapter towards the end on mesophyll conductance.
Very cool. That's a very interesting topic.
I would agree.
I think a lot of people would like it.
I think so too.
Huh. So, first trivia question here. Can you complete this quote? Okay. So it's going to be completing the quote, if you can do it, and then I've revised the quote to fit this chapter.
Oh man. If I get these wrong, are you going to include them? You're going to include me screwing up?
Yes.
Ugh.
I will write
That's
to your
embarrassing.
entire fan fiction fan club.
That is embarrassing. I'm going to get them all wrong.
So, no, okay. Get your head in Dune, in the Dune space, okay? Here's the quote. Fear is the...
mind killer.
Look at that. You were all worried. The new quote should actually be, if we're going to make Dune into this light chapter, shade is the leaf killer. Without light, no photosynthesis shall pass.
That's good.
Yeah. I thought it was pretty good. So, okay, I kind of gave it away, right? We're talking about light today. Doug is going to speak so much about light, shed light on things. There's a lot of puns for this. I won't do that to everybody. But we're past the fundamentals section of the book, and we're moving on to the thinking like a plant. So, chapter 5, light. We know it's important, but broadly speaking, Doug, from a plant physiology, a leaf level perspective, what makes light so incredibly important?
Well, the process under study here is called photosynthesis. So the energy derived from plants is derived from photons of light energy. So it is the fundamental energy source driving all of the reactions we're talking about. So it is fundamental to every aspect of plant physiology.
Well put, first of all, and in the chapter, I don't want to give everything away. We want people to obviously read the book. It's a great resource. But we talk about a lot of different things concerning light, right? So what, for instance, inverse square law, irradiance, direct versus diffuse, like what are some big ticket items that we should be thinking about or consider when thinking about light? And we can take these one at a time, right? So what do we need to know about irradiance? Why is that important?
Where to start? So irradiance really describes the energy incident on the leaf. So there's a lot to think about, both in terms of what that physically means and the impacts it has on driving photochemistry, which is the main interest, I would assume, of most of our listeners.
Right.
So things to think about include the quality of light, which would be the spectral composition of the light, because it will not be uniform across all wavelengths, depending on what the source of light is. And that's something that has critical import for driving photochemistry. Uniformity of the light across the leaf surface being measured is another critical parameter. There's just a whole host of topics that people need to consider when thinking about the light they want to use to drive the photochemistry in their measurements.
You touched on something that I think is kind of consistent throughout a lot of science, not just leaf level gas exchange, but that is using some terminology as a blanket term, right? So we get into this whole, and we don't need to get into units. Units, however, do matter, right?
Right.
But, getting between joules per meter per second and photons, and maybe help me. I am not a physicist by any means, but maybe walk through those differences and why we need to be cognizant of those units and what those
Sure.
actually mean.
Sure. So yeah, I think we'll avoid going into specific definitions, but it's important to realize that, one, not all photons are created equal. So
That was deep. That was very deep.
a lower wavelength photon, let's just say in the blue region, is a lower wavelength compared to a red photon, and that blue photon will have higher energy.
Sure.
So the energy per photon is different across different wavelengths. But the ability to drive photochemistry is not necessarily dependent upon energy, but it may be more dependent upon photon count, which is why the two different units that people can work between are, or some of the different units are energy units, total energy versus total number of photons. And
right.
There's a relationship there, but you also need to know the light quality, the spectral composition of your light, in order to go back and forth between those two units.
What is the best use case for sticking with one or the other?
Sure. So I think in our context for leaf level gas exchange, we really want to be in photon units. And the chapter lays out a biological explanation for that. It's really related to the action spectrum of photochemistry and how that relates to those two different unit structures.
Oh, okay.
So for the majority of our conversation here, we will be considering photon units,
Okay.
which is the SI unit, I believe, is micromoles per meter squared per second.
You believe. Come on. You have that tattoo. It's across your back. Okay, quick pause here. Can you complete this quote? A look of dread washed over Doug's face. The desert teaches men the attitude of the knife? No, nothing.
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 That's the whole quote?
That's the whole quote. No, we'll cut
I
that.
don't know that one.
No, we'll cut that one out.
Is that a Maudib quote? You don't even know. You don't remember.
I don't know. Other than I changed it to the greenhouse teaches plants the attitude of the light, bend, stretch, and thrive toward it.
I love it. I don't know that one.
That's fine.
Oh, I'm sorry. I told you it would be embarrassing.
This episode is ruined. I've ruined it.
So I'm 1 for 2. That's not great odds.
It's not the worst. It's better than me trying to throw paper towels into the trash can. Can you maybe speculate? Maybe you know why, but why or how did the community, or why did we side, I guess, with going towards using PAR?
Sure. So that goes back decades to a lot of research that studied what's considered an action spectrum, where they measured rates of photochemistry as a function of wavelengths of light using very narrow bands of light. And a lot of those data sets concluded that the correct unit to be considering is photons.
Okay. So light, we think of light, it can be used in several different ways, right? Can dissipate its heat. It can be, it's obviously used to drive photochemistry, but then there's also this transmittance and reflectance. And You
Right.
kind of go into some detail about that in the book, but why are those
Yes.
so important?
Yeah, that's a great question as well. Even if you know perfectly the quantity of photons incident on the leaf, and that's the terminology typically used, is striking the leaf surface or incident on the leaf, that is not the same thing as the number of photons available for photochemistry. And that's because not all of those photons will be absorbed. Some of those photons will be reflected by the leaf, so they will strike the leaf and then bounce back towards the atmosphere. And some of them will be transmitted right through the leaf and not interact in any way with the leaf. And so, in order to really understand rates of photochemistry as a function of photon energy, you also need to understand those reflectance and transmittance parameters, which allow you to calculate an absorptance parameter,
Okay.
which tells you of the photons that are striking the leaf, how many of those, what proportion of those get absorbed.
Right.
That's
Okay.
what that absorptance parameter tells you.
So it's incredibly important, right? And I
Yeah,
know that within 6800 methodology and the software and things like, we do try to account for some of this with some standards, which we've talked about in previous episodes. We have preset standards, like you should figure out ways to make those more up to date with your organism, whatever tissues you're looking at. But it's so important. Why aren't more people trying to account for this absorptance?
right. That's a great question, and it's really a function of the cost and complexity of the instrumentation needed to make this measurement. The sort of gold standard for measuring absorptance requires a very stable light source, an integrating sphere that has a coated surface of near perfect reflectance, and a high quality spectrometer. None of which are low cost, none of which are sort of, they all have kind of high maintenance and calibration demands. Right. So, due to that cost and complexity, not many labs are capable of making these measurements, and people use either our defaults or literature values for their species.
Okay. Yeah. So there is a diagram of an integrating sphere, I believe in the chapter.
There is, yes.
And yeah, it's like not exactly super easy and
It's not.
fun to use.
Yeah, it's not a trivial measurement, especially the measurement itself is not super complex, but it's understanding the setup and even creating the setup in the first place is a bit complicated. So it's not done as maybe often as at least we would like.
But having large ramifications on the biology.
That's right. Yeah, these are really critical nuances that really can impact some of the parameters that are calculated.
To give some logic to this universe.
That's right.
Which reminds me of this quote from Dune. Deep in the human unconsciousness is a pervasive need for a
logical universe.
Wow. You are good. You are good. However, I'll counter that with the plant example. Deep in the plant unconsciousness is a pervasive need for light to seek and roots to drink. I knew you'd like the roots.
Very nice.
I knew.
Very poetic.
Well, I've been called lots of things. A poet's not one of them. So it's safe to say that light obviously has this huge impact on leaf level physiology and on all aspects of plant biology, but specifically with leaf level physiology. And there's a few things that we really emphasize with gas exchange instrumentation, right? That have huge light dependencies. That being transpiration and assimilation, and we frame them in terms of light quantity and quality, which you've already touched on. But maybe you could give some examples. Some of them are in the book, but some examples of what happens when that quantity and quality are manipulated.
Sure. So I think a well-studied example is the location of blue light receptors in guard cells of stomata. So if you were to do an experiment with a leaf-level gas exchange system and only supply red light, so only have red LEDs without any blue light contribution, it will become very evident that the stomata will respond to that by shutting down. So there needs to be at least a small fraction of blue light for most measurements to keep those stomates open. And another sort of caveat here to remember or to keep in mind is these responses to light have varying kinetic properties. And so you're not going to, if you put a leaf in a chamber and shut off the blue light, you're not going to instantly see the stomates shut down. These things can take many, many minutes. And that's important to keep in mind as well.
Only red and only blue, right? You see these odd things, but are there other common methods, common or I guess maybe uncommon methods to kind of investigate light impact on physiology?
So I think one common thing, or one thing to keep in mind, especially with use with a fluorometer, is in our case, the 6800 fluorometer has red LEDs that are used for the measuring beam and the saturating flash. And because of that, it's best practice to use that same wavelength of LED for the actinic light, the light driving photochemistry. But you still need a little bit of blue light to keep those stomates open. So there's a balance there, and our default is to use 10% blue light and 90% red light for the actinic light, which kind of gives you the best balance of those competing needs.
Last episode, we talked at great length about being very cautious of using defaults. However, I do think that this is one of those defaults. It's actually really pretty good to start with.
I think so. It's a good starting point for many questions. Now, that doesn't say there aren't really interesting questions where you would vary the light quality. So you could do experiments where you examine your particular study system with different ratios of red and blue light. And that's certainly a valid experimental protocol, and interesting questions can arise as to how different plants respond to different qualities of light.
So yeah, changing the quality and quantity of light is something that's really great. And I think most users are aware of running something like a light response curve, where you can derive some of these really key and interesting physiological parameters, which we don't need to get into. They can read that in the book. But it brings up a good point, and this is not to serve as a billboard for the 6800, but with those background programs, like what are some things, Doug, maybe off the top of your head, that you could think of constructing a program to manipulate some of these things?
Sure. So I think the most common is, a default program would be a light response curve, where you are simply changing the intensity of light stepwise over a period of time. But some other interesting things that users could do is changing the quality of light in a background program, for example, and that's completely customizable. You could also interact changing light intensity with other parameters, such as temperature or CO2. So these other parameters will certainly interact with light intensity and can be customized into really any program a user wants.
That's a lot of manipulation that can happen in the chamber and with the system, which is a really great thing, kind of creating and running your own sub experiment, so to speak. And so in the book, we do talk about light response curves. We talk a little bit about these programs, and other than being out in the field or greenhouse and inadvertently blocking the light source while you're measuring, which we don't need to name names or point any fingers. It's no one here. Other than getting into some of that, which we don't need to, I think the big things that I would really love your perspective on, and things I think all of the incredible listeners would like to know more about, Dougie Fresh, is this concept of uniformity and leaf angle, which I know are a couple of things that you really, really love. So maybe, just get into what are those and why do they matter, and
Sure.
what we've done to address them.
So everything we've discussed in terms of light incident on the leaf, all of the parameters derived from photochemistry. Let me just start over.
You're doing great. I support you.
Okay. So we've talked a lot about the importance of knowing your light intensity, because that is an important parameter to drive photochemistry. But another component of that is that the light is uniform across the surface of the leaf being measured. And so that's a really important engineering exercise for companies that are designing gas exchange instruments. And we took great lengths to quantify the distribution of light in our chambers to make sure it's as uniform as we could possibly make them to ensure reduced errors in your measurements.
I have never seen so many documents. I'm looking at a square or a circle, and I'm colorblind, so it's all gray or less gray. Or we really do take uniformity incredibly serious here.
Very much so, because it can lead to large errors in your measurements if you've got big changes in light intensity across the surface of that leaf, which is very evident from light response curve measurements. It's a critical parameter, and so we try to make it as good as we can.
And so that speaks to the tedious nature of a lot of people like yourself, engineers, and those interested in biology. And so we talk a lot about that in the chapter, but I don't want to say it's a passion. I don't want to get into your headspace here, but I know that the importance of leaf angle is near and dear to your heart.
Absolutely, it is. So a goal of many measurements with gas exchange is to sort of match the environment the leaf was in your chamber prior to you clamping on the leaf. That's typically a goal for survey measurements. And the light intensity is one of those parameters you really should match as close as possible. Mm-hmm. Now, how do you know the light intensity on a leaf? And we do this exercise when we give trainings. If you take your quantum sensor and hold it next to a leaf, but hold it straight up and down, you might get an answer that doesn't match what that leaf is seeing if it is at an angle that's different than normal to the sun. That leaf angle with respect to the light source follows a cosine law that we discuss in the chapter, where light intensity can fall dramatically as that angle changes. And it's a really important thing to consider. So when doing survey measurements in one spot where it's absolutely critical to either measure your light in that angle with the 6800 or using the 600, it's really important to maintain that same angle of light intensity while making the measurement. And we actually have hardware in place in the LI-600 to measure the angle of the instrument and using GPS information, calculating that angle of incidence from the leaf with respect to the sun for every measurement. And that's a really important corollary parameter to explain the model conductance for one, but also chlorophyll fluorescence is greatly impacted by that light intensity.
It is wild to see that in the data, like to plot that later. Like it is.
It's a really, really useful parameter to understand your data, especially when you go out with the 600 and you can make dozens to hundreds of measurements. That's a really important explanatory variable.
Right. I mean, in every intro to plant biology or botany, some of these other courses, right? Phototropism is that's one of those big
Absolutely.
things that is covered, and actually being able to see that and track that is pretty remarkable. Lastly, to kind of close things up, because Doug is a very important man. Maybe you could talk about some of the big takeaway items from this chapter. Like, what should the Phys Fam take note of so they are using, harnessing light correctly?
So yeah, I think there's a couple of key takeaways here. One is to really understand what it is a quantum sensor measures and reports in terms of the quantum energy, not the radiometric energy. So understanding those differences is important. Understanding how light impacts photosynthesis, both from an incident perspective and we talked a lot about absorptance. The absorptance parameter is really critical here that a lot of people ignore and use our defaults that we have built into the instrument. And that's not necessarily the right answer for your leaf material. So those are two big takeaways. And I think that's all I got.
Know the equipment, know what you're actually measuring. These are themes that carry throughout the book. But Doug gave some great advice, and it's, do not fear. And why should we not fear, Doug? We should not fear because fear
is the mind killer.
Thank you, Dr. Lynch, for joining me today. And thank you for everyone else who joined us today on this podcast. Please take some time to read the chapter. It should now be available. And please remember to like, subscribe, tell your friends, tell your family, and please stay tuned for the next episode that will be available in about 2 weeks. Until then, stay curious, stay kind, and I'll talk to you soon.